Numerical number 7, Kinematics 3. A body projected vertically upwards from the top of a tower reaches the ground in t1 second. If it is projected vertically downwards from the same top with the same velocity, it reaches the ground in time t2 second. If it is dropped from the top, it reaches the ground in t second. Prove that t equal root over t1 dot t2. Numerical number 7. A body projected vertically upwards from the top of a tower reaches the ground in t1 second. If it is projected vertically downwards from the same top with the same velocity, it reaches the ground in t2 second. If it is just dropped from the top, it reaches the ground in time t second, such that we have to prove that t equal to root over t1 dot t2. This is the top of a tower. This is the top of a tower from which a body is projected vertically upwards with the velocity u. A body of mass m will be projected from the point A, that means from the top of a tower with the speed u, vertically upwards, and it will strike the ground. It will strike the ground at this point in time t1 second. The body will strike the ground at this point in time t1 second. Similarly, same body is dropped with the same speed u from the top of the tower with the speed u2 equal u, means it is dropped with the same speed u2 equal u, and it will strike the ground in time t2 second. It will strike the ground in time t2 second. Same body will be dropped from rest. Same body will be dropped from rest. That means initial speed u3 will be equal 0, because the body is dropped from rest, and it will reach the ground, or it will strike the ground at this point in time t second. And h is the height of the tower. H is the height of the tower, which is equal to an. H is equal to an. When the body is thrown vertically upwards, with a velocity u, 1 equal u, when the body is thrown vertically upwards with a velocity u1 equal u, in that case the distance traveled by the body in downward direction, will be h, small h, that will be the height of the tower, will be small h will be equal to which equation we have to use? V equal u plus at, or s equal ut plus half at square, or v square equal u square plus 2a dot s. In this case, distance versus time related equation is h is equal minus u1 t1 plus half plus g t1 square plus g t1 square. From the top of the tower, it will reach the maximum height, and the distance traveled by the body is capital H before returning to the point A, and during downward motion it will traverse the same distance, so resultant displacement will be h minus h. During upward motion it traverses capital H distance, but small h is the height of the tower, so hence total displacement for the first case will be h minus h plus small h. Capital H minus capital H, that means during downward motion displacement will be minus capital H, because we are considering downward motion of the body. And during downward motion, when a body is projected upwards from the top of the tower A, it traverses capital H distance, and when returning to the same point it will traverse the same distance capital H. During upward motion it will traverse minus capital H distance, and during downward motion before returning to the top of the tower it will traverse capital H distance, and capital H will cancel minus capital H. and resultant displacement will be what? Minus h plus h small h. From the top of the tower, that is from the point A, during upward motion, it will traverse minus h distance with respect to downward motion of the body. It will traverse minus h distance, and before returning to the top of the tower, it will again traverse the same distance, capital H. And as we are considering downward motion, acceleration will be plus g. Acceleration will be plus g. Finally, we get small h, that is the total displacement during downward motion of the body, will be equal to minus u t1 plus half g t1 square. Small h is the height of the tower, and that is also the displacement of the body during downward motion of the body for the first case, which is equal to minus u t1 plus half g t1 square, which is equation 1. And here we are considering minus u1 because we are considering downward motion of the body and the body is projected upwards. That's why the speed will be minus u1. Again, we can say that for the first case, total displacement will be what? If we consider downward motion, then plus h plus small h, then plus capital H, then minus capital H, minus capital H. That means total distance will be minus capital H plus capital H plus small h. Minus capital H for the upward motion of the body when it will reach up to the maximum point, and capital H is considered when it will return to the top of the tower. Now for the second case, the body is dropped with the speed u2 equal u, and we have to consider the equation of motion using the equation S equal ut plus half at square. Using the equation S is equal ut plus half at square. In downward direction, using S equal ut plus half at square in downward direction. For the second case, in which the body is dropped with the same speed u2 equal u. Using S equal ut plus half at square in downward direction for the second case in which the body is thrown downwards, we get h is equal u2 t2 plus half g t2 square, u2 t2 plus half g t2 square. Therefore h is equal u t2 plus half g t2 square. That is equation 2. H is equal to u2 t2, u t2 plus half g t2 square. For the third case, when the body is dropped from rest, h will be equal to u3t plus half g t square. H is equal 1 by 2 gt square, since u3 is equal 0, as body is dropped from rest for the third case. H is equal to 1 by 2 gt square. That is also the height of the tower. Now we have to prove t equal root over t1 dot t2. Multiplying equation 1 by t2 and equation 2 by t1 and adding them, we get ht2 plus ht1 as equal minus u t1 t2 plus half g t1 square t2 plus u t2 t1 plus half g t2 square t1, or comma h is taken common under bracket t1 plus t2, and half g t1 t2 is taken common under bracket. There should be t1 plus t2, and in this case minus u t1 t2 and plus u t2 t1 will cancel out, and we get h t1 t2 as equal half g t1 t2 t1 plus t2. So finally we get h as equal half g t1 t2, h as equal half g t1 t2, which is equation 4. Comparing equations 3 and 4, we get half g t square as equal half g t1 t2, as both are equal to h, and therefore t is equal to root over t1 t2. T is equal to root over T1 T2. Hence it is proved T as equal root over T1 T2. That is time required by the body which is dropped from rest reaching the ground is T, which is equal to the square root of product of time required by the same body which is thrown vertically upwards, and the time required by the body to reach the ground which is dropped from the same height or from the top of the tower. That means T is equal root over T1 T2.